All right, let's just dive right in. We're about to go on a wild journey through some of the most mind-bending ideas in all of physics. We're going to follow the math of Albert Einstein to its absolute, most extreme limits and see what it really says about the fabric of our universe.
So let's kick things off with a question that sounds simple, but has an answer that is anything but. Seriously, what do you think actually happens if you or your spaceship fall past that point of no return into a black hole?
And here's the twist, the absolute kicker. The answer, it completely depends on where you're watching from. What a person floating safely far away sees is totally fundamentally different from what the person actually falling in experiences. And that one single paradox, well, it unlocks everything.
This leads us straight to something called the frozen horizon paradox. And it's one of the first really bizarre things that popped right out of the general theory of relativity, which is, of course, our best blueprint for how gravity works.
Okay, so here's the scene. Imagine you're watching a friend's spaceship fall towards a black hole. You'd expect it to just zip past the edge, right? Wrong. Instead, you'd see the light from their ship get stretched out, turning redder and dimmer. The ship itself would look like it's moving in slow motion, grinding to a halt right at the edge, frozen in time. From your point of view, it would take an infinite amount of time to cross, fading away until it's gone, but never, ever making it inside. How weird is that?
To really get our heads around why that happens, we need to hit rewind for a second and talk about what gravity even is. Because that paradox isn't a mistake in the math, it's a giant clue telling us we need to think about gravity in a completely new way.
Even Isaac Newton himself, the guy who literally wrote the book on gravity, was super bothered by his own theory. He couldn't wrap his head around how the sun could just reach out and pull on the Earth across millions of miles of totally empty space. He famously called it spooky action at a distance, an absurdity. And this is where Einstein's genius just changes the game completely. He didn't see gravity as a spooky force at all. He saw it as part of the geometry of the universe. The physicist John Wheeler put it perfectly. Matter tells space-time how to curve, and that curved space-time tells matter how to move. It's all just geometry, no spooky action needed.
So Einstein drops this revolutionary new theory on the world, and physicists immediately start trying to solve its equations. And almost right away, they found some absolute monsters lurking inside the math.
Get this, just 1 year after Einstein published his theory, a German physicist named Karl Schwarzschild found the very first exact solution to the equations while serving in the trenches on the front lines of World War I. Insane, right? And his solution predicted two absolutely terrifying things: a singularity, a point of infinite density where physics just breaks, and an event horizon, a one-way door you can never escape.
Now, for decades, a lot of scientists thought these black holes were just a weird quirk in the math, that they couldn't be real. But then, physics showed that for the biggest stars out there, anything more than about 2.1 times the mass of our sun, there was no other option. When they die, there is absolutely nothing that can stop them from collapsing forever. Black holes weren't just possible, they were inevitable.
Okay, so we've established black holes are real. But that just brings us right back to our original problem. How can a spaceship both freeze at the edge of a black hole and fall right through it at the same time? Well, the answer has everything to do with what kind of map you're using to chart the journey.
So here's the big secret. The frozen horizon paradox isn't a physical paradox at all. It's a distortion, an illusion, created by using a specific kind of map, a coordinate system, that just happens to break down right at the event horizon.
Think about it like a map of the Earth. The Mercator map we all saw in school is great for sailors because it keeps the angles right. But it makes Greenland look absolutely enormous, as big as Africa. Then you've got another map, like the Gall-Peters, which shows the true sizes of the continents, but it really warps their shapes. Neither map is wrong. They're just different tools that show the same round Earth with different kinds of distortions. It's the exact same idea with maps of space-time.
So the event horizon is not a physical wall in space. The frozen view is just a distortion you get on the map that we use from far away. For the person who's actually falling in, they're using their own local map. And on their map, they sail right across the horizon, probably without even noticing. Both descriptions are totally correct, from their own point of view.
So now that we have better maps that don't break at the horizon, we can finally see the complete, totally mind-blowing picture that the math was trying to show us this whole time. And let me tell you, it reveals things that are way, way stranger than just black holes.
When you take the math for the simplest possible black hole and extend it as far as it can possibly go, you don't just get a black hole, you also get its exact opposite, a white hole, a place where things can only fly out, never in. You get an entirely separate, parallel universe, and you get a tunnel connecting our universe to that one, a wormhole. This all just falls right out of the simplest solution.
Now, before you get too excited and start packing your bags for another universe, there's a pretty big catch. This particular kind of wormhole is incredibly unstable. It basically appears and then pinches itself off so fast that not even a single photon of light could make it through to the other side. So, no interstellar travel here.
But wait, that was for a simple, non-spinning black hole. In reality, everything spins. So what about a realistic rotating black hole? Well, in 1963, Roy Kerr solved those equations and the inside is completely different. The singularity at the center isn't a point anymore, it's a ring. And there aren't one, but two event horizons to deal with. So what would that trip be like? Well, first, you'd cross the outer horizon. That's still the point of no return. But then you'd cross the inner horizon, and suddenly you can move around again. You're not doomed to be crushed. In fact, if you aimed just right, you could theoretically fly right through the center of the ring and pop out into a new universe.
I mean, come on, this sounds like pure science fiction. A gateway to another universe? So we have to ask the big question. Could any of this, white holes, stable wormholes, parallel universes, could any of it actually be real?
And unfortunately, this is where reality hits pretty hard. These solutions describe perfect, eternal black holes that have existed forever, not the messy kind that form when a real star collapses. Most physicists also think that inner horizon would be incredibly unstable, slamming shut the moment anything tried to cross it. And to top it off, any wormhole you could actually travel through seems to require something called exotic matter, stuff with negative gravity that pushes things apart. We have no evidence it even exists.
But let's just end on this one thought. For 50 years, the greatest minds in physics, including Albert Einstein himself, thought that black holes were just a fantasy, a weird quirk in the math that couldn't possibly be real. And they were completely wrong.
It really makes you wonder, doesn't it? What other impossible ideas are lurking in our equations right now? Things we're dismissing as just a mathematical fantasy that might one day turn out to be a real fundamental part of our universe. What impossible math of today will be the reality of tomorrow?